Okay, so let's try this again now that I'm recording. My name's Ryan O'Donnell, and I'm a second-year master's student in operations research and industrial engineering. And I'm going to talk today about the homework for Stats 371. And this homework primarily discusses logistic regression. It talks just a little bit about some model selection tools, but for the most part, it covers logistic regression. You might have noticed if you've looked at the practice tests that model selection is not as big on the exam as logistic regression is. Okay, and logistic regression at its core is a really important idea, right? Because so far up to this point in this class, we've talked a lot about how to make linear models, which are great, except for the fact that they don't work at all if you're trying to predict something that is binary. So, and there's all the time we have to predict something that's binary. We might want to be predicting whether or not someone will buy a product. We might want to be predicting whether or not someone will be maybe a Republican, to try to help do some predictions on polling, for example. And there's a whole, you can imagine many things that, would require an approach more like logistic regression. Okay. So I'm going to be using a data set about wine, and I think it's just kind of a fun data set to go through, but the data set is decently big, and I'll post it, but it's about 6,500 wines, and we're going to predict whether or not the wine is red or white based on a whole bunch of factors about the wine. Things like the sugar content of the wine is available, the acidity is available, and about 10 other things are available. And this is going to work really well. So I'm going to accurately predict whether or not it's red or it's white, something like 99.5% of the time. And that shouldn't be very surprising to you because there's probably a bunch of underlying reasoning about how the wines work, and red wines tend to be more acidic and white wines tend to be more sweet, or something like that. Okay? So in real life, you're never going to predict something. You would not really care about predicting something like this because it conforms really well to some, like physical and physical laws, pretty much. But I'm just going through it because it works really well for the purposes of an example. Okay, and in this data set, red is interpreted as R to be 0 for the purposes of whether or not it's a 0 or 1 in the logistic regression. Okay, so before I really get going on this, does anybody have any questions specifically about like why we do logistic regression, or why we have to come up with this huge complicated thing to deal with this problem of having a binary response variable? Is everybody pretty comfortable with the whole like underlying reasoning and things? Do people want me to so I can just jump through and kind of go through how to do this sort of thing in R? Okay, sure.
Can I ask a quick question?
Sure.
I actually have some already, but is this going to be posted on the YouTube?
Yeah, it'll be uploaded to YouTube. Yeah. Okay. Lost my train of thought a little bit. Okay. So, I'm just gonna, in terms of R commands, I can talk about them if you'd like, but it's pretty much just like this is how you do this sort of thing in R. But so we can look at this. We can actually look at this wine data set a little bit, and that's just a nice command that you can run to pull off the very first data point. So there's a whole bunch of different things in this data set, like the acidity, the citric acid, the sugar content, sulfur dioxide. I don't really know very much about wine. It's just kind of a fun data set. So there's a whole lot of variables we can use. You got a question?
Is this available too?
I'll post it. I'll post it later if that's okay, so you can follow along. Yeah. So the important thing about R, so in terms of running these R commands, you have now instead of using LM, you're using GLM, which stands for generalized linear model. The generalized linear model function will do lots of different things for you, so you have to make sure that you tell it what you want, and it's that your family is binomial, which if you do that, you'll generate the correct form of logistic regression. So in the text, it talked about this thing called the logit model, right, which was the log odds. So it's like the log of p over 1 minus p. And there are other things you can do other than the logit model. There's like things called a probit model and a few others, but the logit is very common, and the probit is probably the next most common. And for the purposes of the course, we're only going to talk about the logit. So, Yeah, so you can actually just do this and create a generalized linear model really, really quickly. And let's just go ahead and look at that. So I just made a really simple logistic regression model that regressed the type of the wine on the residual sugars in the wine. Okay, and for the most part, this looks very similar to what we've seen so far, right? We have some coefficients, we have some p-values, but then we have some other things running around in here too. It automatically comes back with the AIC, which is something we talked about in the model selection readings. It comes back with this thing called null deviance, this thing called residual deviance. So there are definitely some clear differences, right? Okay. And we'll kind of talk about those things in turn in just a moment. Okay, but it's also really important, right, to be able to kind of visualize your data. So, as I'm sure you all know, would you rather see pictures or would you rather see a lot of numbers? You'd rather see, yeah, thank you. You'd rather see pictures, right? So we always have to find ways to make pictures, and one of the easiest ways to do that is with box plots. And there's other ways you could do this too. And for the purposes of the homework, really anything that works fairly well would be fine. So if I make this box plot of the wine content versus or the wine type versus their sugar content, you get this nice little box plot. And it looks a little funny over here in the red area, just because that's kind of how the data set works out. Okay. And if you want to see one that's a little bit nicer looking, we could do the same thing with the fixed acidity. And hey, that one looks quite a bit nicer, right? So you can already see that generally speaking, the reds seem to have a higher median in terms of fixed acidity than the whites. And so we can kind of get a sense of some of the things we could expect to have happen in the logistic regression. Okay. Everybody okay? Doing great, no questions? Nobody's come up with a question about the underlying parts of logistic regression in the last 5 minutes? Okay. All right. So I will just lecture through and kind of talk through the homework. Please stop me if you have any questions at any point. Really, if anything comes up, just let me know. Okay. So again, we're going to continue on with this example of doing the wines against the residual sugars. And so we have these different estimates, and we'll talk about those more in a second. So let's actually generate this curve. So one of the big parts about logistic regression, right, is that you're not trying to predict. At the heart of the idea is you're trying to predict the probability that this data point will be of, type 1 or type 2, right? And so we can generate a curve that represents the probability function. And, we can do that with this curve command, and it's talked about, I think, both in the lectures and on the R help pages as well. But really all we're trying to do here is give it this nasty looking function, right? And the reason, so just to make sure everybody's okay with this, so we always have, so that's just the single variable logistic regression, right? The log of p over 1 minus p is equal to beta 0 plus beta 1 x1, right? And you can simplify this with some pretty straightforward algebra if you want. And then, so you take the exponent of both sides. You can put 1 minus p times that, right? And then start solving for p. Everybody okay with that? Okay. And you can end up showing that this is true. So you can end up showing that the probability should be e to the beta 0 plus beta 1 times x1 over 1 plus e to the beta 0 plus b1 x1, right? And that's just some straightforward algebra. If you want me to do that, I can. But that's where this function is coming from. Okay, so we're getting the beta. Oh, there should be a 0.2. Let me fix that real quick. Should look a little nicer now. Not really. Okay, so you know that's the B0 term, right? And that's just coming from where? Yeah, that's just the intercept term that we're getting, just like before. And then that's the B1 term that we're getting from there as well. And so you can just call that with the curve function, and you get this thing, right? And does this look like what we would expect it to look like? Anybody? So what do we usually? So we usually expect like this logistic regression to make what kind of shape? All right, so we usually expect it to look like an S, right? So that's something, and you can see pictures of it in the readings. But we usually expect it to make a nice little S shape where probability is really low and starts gradually, you know, the change in the probability starts getting faster and faster as we move from left to right. It goes up very quickly in the middle, and then it starts to balance, starts to top out. However, you'll notice that it doesn't look like that in this case, but that's really because I picked the bounds on that graphing function. So if I change those, so instead of going from 0.6 to 65.8, instead I go from like -20 to 20, we get a much nicer looking S, right? So don't be surprised when you graph these things if they don't make like nice S shapes. That's totally okay. Check your bounds. If you can't make it create an S shape regardless of your bounds, you might have a problem, but generally it should be fine. Okay? Is that all right? Okay, so yeah, so usually with logistic regression, and you know, in real life we can't have like a negative residual sugar, but for the purposes of math, as you move from left to right on the sugar axis, it doesn't increase very quickly, and then it starts increasing very, very quickly, and then it kind of tops out. Right? Okay. All right. I'm going to look at this summary one more time. Okay, everybody okay? All right, so the other thing I want to point out is different, you know, we've got to talk about these, so these coefficients that come out are not the same thing as what we got before. They're much more complicated, right? Because the whole point of logistic regression is that now we're regressing these log odds on beta 0 plus beta 1x1 plus beta 2x2, et cetera, right? So this is pretty ugly, and it doesn't have a great interpretation unless you're willing to kind of work through it and, you know, plug numbers in, if you will. So this estimate, right, this 0.3404, right, that corresponds to a change in what? Does it correspond to a change in the probability that it's a red or a white wine? Yeah, okay, so good. Yeah, so it corresponds with a change in the log odds. So if you increase the sugar count by 1, right, then the log odds of whether or not it's a red or a white wine will change by 0.3404. Great. So that's all good, and maybe you think in terms of log odds. Basically, most people do not think in terms of log odds, though, right? We prefer probability. And if you're used to playing, you know, if you gambled a little bit, that's a sort of a thing where you'll see odds much more frequently, right? So maybe you're used to seeing odds a little bit more. But we can always kind of work through this. We can always kind of plug it through in these equations and sort of get corresponding changes in odds. But it's really awkward to plug it in here and get the corresponding change in probability, but it's doable, okay? Usually it's fine to report just the changes in the odds, all right? So is the change in the odds, is it additive? So the change in the log odds was additive, right? So You went up and with residual sugar, you changed residual sugar by 1, and the log odds went up by 0.34, right? So is that the same thing in terms of just the odds? Does it change additively? Or does it change in some other way? Okay, so let's talk about that, right? So let's just try to plug some things in here and see what happens. So I'm going to erase this. Can people actually see? So there's some people in the back, right, who are in 371. If I write here, can you see? Okay. So on one hand, we had exp of beta 0 plus beta 1 x1, and then on the other, we have e raised to the beta 0 plus beta 1 times x1 plus q, where q is just some change. So maybe you went up in sugar content by like 5. Okay? So let's kind of work these things out. So this is this, right? E to the beta 0 plus beta 1 x1. And if you remember all those exponent rules from probably a really long time ago, this is the same as e to the beta 0 times e to the b1 x1, right? Okay? So we can do the same thing over here, right? So what do we get on the right side? Anybody? And you don't have to go all the way to the end, but what do you get on the right side if you work through with the same exact exponent rules? Okay, so that's true, right? So that's just e to the b0 plus b1 x1 plus b1 q1, right? So then by exponent rules, it's this. Right, so it's e to the b0 times e to the b1 x1 times e to the b1 q1 now, right? Is that okay? So on one hand, we just had e times e to the beta 0 times e to the b1 x1. And on the other hand, we have the same thing, but times some other value, right? So now changing sugar when you're looking at the odds doesn't change it additively, right? You don't add some number, but you do what? You just, so you just multiply by some value that's equal to that. Okay? Is that all right? And that's where that idea of like an odds ratio came from that's talked about in the text and I think talked about in the lectures as well. Is that all right? So if you're trying to interpret how it changes the odds, you should expect that there's some multiplicative thing happening. All right? And in addition to the multiplicative term, there's also e to the power of something, right? So there's also some exponential growth in a way. Okay. All right. Okay, I promise we're done doing math, for now at least. I think for the rest of this actually. But that's one way you can actually get at these coefficients and then interpret them in a way someone can understand, right? Because you never want to tell somebody, hey, your log odds are going to increase by 0.05 if you do this, right? Because no one's going to know what you're talking about. You have to give it at least in terms of odds because that's something you can explain to someone. Okay? All right. Okay, so now that we've talked a little bit about the coefficients, so everything else is nice. You might notice something seems a little weird, which is that now you have a z value instead of a t value, right? That's totally okay, don't worry about that. When you do logistic regression, you can do a z-test instead of a t-test, which is what we've been doing up till now. And you can just accept that. If you want to know why you can do a z-test instead of a t-test, just talk to me later. So the result is that the probability, or the p-value, is a really small number, right? So does that mean that this variable is statistically significant? Or is it not statistically significant? Okay, I have a head shake yes. So it is statistically significant? Yeah, and it is. Okay, so you can interpret that just like normal. So as long as that value is really small, great. That's a good thing. Okay. But there's a problem, right? Which is that especially when we start doing logistic regression with more than just one x variable, we were still concerned before with whether or not maybe the regression as a whole was significant, and we were also concerned with how good the power of this regression was. And you know, if you wanted to look at how much the variation was being explained before, when we had just ordinary linear regression, right? What did you look at? Anybody remember? Yeah, you looked at r squared. And r squared was great. It told you how much of the variation in y was explained by your collection of x variables. But it turns out now we don't get to have that anymore. And so there's not necessarily, so there are various ways you can get at something akin to r squared, but it's not really straightforward. We're going to stick with, we're going to stick with McFadden's pseudo r squared, okay? Which has to do with these deviance terms, and there's just a formula for it, more or less, which is that it's 1 minus the model's deviance divided by the model's null deviance, and the model 1 deviance is the same thing as this. Okay, it's the same thing as residual deviance. Okay, but you can call it through R by just doing model 1 $ deviance, right? Because the dollar signs tells R, hey, go and get me that part of whatever object I'm looking at. Right now I'm looking at model 1, so if I call the dollar sign, it'll give me model 1's deviance. And deviance is just a mathematical way to check how well the model is doing, more or less. There's more information in your text if you want. It has to do with the log likelihood, which is a topic I don't think you're really very familiar with. If you are, great. If not, it's not a big deal. But it's just another statistical term. So we can actually generate this thing's pseudo r squared, right? And we get this value out. It's 0.1579879. Okay? Is that all right? So that's something you can look at to compare models. There's other ways you can compare models too. We'll get to that right at the end, and we'll get there soon. We'll be able to move a little faster now that we've kind of moved through some of the more time-consuming parts of this. So is that good? Do you have a question? Sure.
The lower the better, or is it?
It's the higher the better. It's just like traditional R squared. So usually, information criterion like AIC and BIC are better when they're lower, and it is better when they're lower. So like -100 would be better than -50. You can have a negative AIC. That's a good thing, actually. So, but unless it it should just be information criterion that are considered lower, that are considered better when they're lower. But so what was a good R squared before? I'll get to your question in just a second. What was considered a good R squared before? Anybody?
Something high.
Yeah, something high. Great. So something maybe like 70, maybe like 0.7 was good. This is a little bit different. Interpretations can vary some, but usually that number is pretty good between like 0.2 and 0.4. Okay? And that's something that wasn't discussed in the text. I don't think you really have to worry about that. But if this ever comes up for you, the person who made this test generally considered it good as long as it was between 0.2 and 0.4. So unless there's been some more modern things done on it, that can be considered a pretty good value. So this one's not quite what we would consider good, but it's not that far either. Okay? So you have a question?
Wait, so based on what you just said, does that mean if we got a pseudo R squared of like 0.7, that would be like...
That's great.
That's awesome?
No, that's great.
Okay.
Yeah, it's not concerning that it's really, really high. That's just very, very good.
And is that...
So,
the R, but specifically with the pseudo R squared, is that relative to something else? Like, are we using it as a base of comparison, or is it just kind of implicit?
So it's sort of just implicit in the model. You're a bit worried about doing comparisons with it because, again, it doesn't bring in how many parameters are in the model. So it has that same problem where before, right? Where with ordinary linear regression, we wanted to compare something like the adjusted R-squared or the AIC because that took into account how complex the model was. So you don't necessarily want to use this for model comparison, but it's just like, hey, how good's my model doing?
Okay.
And we'll show another way you can do that in just a second. Sure.
Does it increase as you put more variables in?
Hopefully, it will increase as you put more variables in, yes. So, you know, just like R-squared, if you add more variables, it should go up. And this will go up, yeah, even if the variables you add aren't really that important, it'll go up too, just like R-squared would go up if you added variables that weren't very useful. Okay, so, all right, anybody have any more questions? Everybody doing okay? Okay. So, more things. So again, we really want to just get to a point where we can do the same things with logistic regression that we did before with linear regression. So the next kind of thing we were concerned about is how do you build a confidence interval, right? So there's one thing I want to point out. Do you think it makes a lot of sense? So in the end, we're going to be predicting whether or not it's a red or a white line, right? And we're going to be predicting that based on the probability that we get out at the end of the prediction. So, you know, if we predict that there's a 60% chance that it's a red line, then we'll say, yeah, it's a red line. Okay? That makes sense? So the problem is it doesn't really make a lot of sense to build a confidence or a prediction interval around that binary prediction, right? Because, you know, you're predicting a 0 or a 1, and we usually think that our confidence intervals are distributed how? So what's the distribution of our confidence intervals in linear regression? Right. So what did we like our so when we looked at our residuals way back in linear regression, right? It was one of those assumptions, those core assumptions of linear regression was that the residuals have what kind of distribution? Normal? Somebody say normal. Yeah, so it's that they have a normal distribution. And you want your confidence intervals to have a normal distribution as well. And if you're predicting something that's binary, it's not going to have a normal distribution, right? Because a normal distribution is continuous and your prediction is a 0 or a 1, so that doesn't make a lot of sense, which is why we choose to build our prediction, our confidence and prediction intervals around the probability itself. Okay? So as far as I know, there's not a straightforward way to do that in R, but that's one way you can. This is one way you can do it. So you can call predict. So you can call this predict function and give it your model. And give it some new data, and this is just something I picked. I said, okay, the residual sugars are going to be 7 for this new data point. And then something that's very important is that you give it type equals response, because if you give it that, then it will give you your prediction as a probability. It won't give it to you as like a log, or as a log odds. It's much easier to work with your probabilities. And then you'll notice that I just added this little thing on the end that says standard error dot fit or se.fit equals true, and that way your prediction just keeps track of the standard error from your model from up above, okay, and estimates that standard error, right? Because we build our confidence intervals based on your standard error. If your standard error is very big, you're going to have a big confidence interval, right? Because you're not very confident in your prediction. So you can do this, and so you can take your prediction, right? If you want the upper side of the confidence interval, it would just be your prediction plus, so it would be 1.96 if you wanted a 95% confidence interval. In this case, it's 1.64, I think, because I think that's a 90% confidence interval. Okay, and that's just the z. That's just coming from a z table. So you can always look these values up in a z table if you would like. Okay, and then the lower side of the confidence interval is the prediction minus that term, so that 1.64 times the standard error. Okay. And if you do this, you find out that we are guessing that a wine with that much residual sugar has a probability of about 0.89, and the upper part of our confidence interval is 0.908, and the lower is 0.888. Okay? So something that's good to point out here, right, is that it might be really concerning if your confidence interval contains 0.5, right? Because if your confidence interval contains 0.5, then you're not really able to say with a certain level of confidence that, yeah, that thing's a red wine, right? There's a chance that there's a chance even within our confidence interval that in fact it's a white wine, right? Does that make sense to everybody? Everybody doing okay? All right. Okay, so, all right. So if that's okay, sure.
Where'd you get the 1.64?
So that's just the z value for a 90% confidence interval. Your 1.96 is the equivalent for a for 0.95, and I think I'll try to remember. There's a command for that in R. I have to think about how to do it in R, but you can call the z table in R. So she had a question first. Oh, that's model 1. Sorry, I know that's hard to read. That's model 1 comma new data. So you don't need to say new data equals, but I did because it's one of the arguments that's passed to this function. So I'm just saying, based on model 1, and I want to make a prediction about some new data, and my new data is going to be one data point with residual sugar equals 7. Okay. No, I don't think you need list. I think list is only there if you want to give it multiple. I can try. I don't really remember. I mean, if it doesn't work, then it needs list. Okay. Yeah. Okay, so apparently you need list. So I took it out, it didn't work, so I guess you need list.
Is this confidence or prediction? Okay. Because you specify what the value would be of a residual sugar, right?
Yeah, so usually, the big core difference between a confidence interval and a prediction interval in linear regression mathematically is that the standard error formula is different. Right? So the standard error formula is literally different, and you can look up the standard error formula if you want. It's just a formula. There's tons of reasoning behind it, but whatever. I think that's prediction.
Just because there's a question.
Yeah, there's a question. I know, and that's why I'm doing this. You'll find that this should match up very well with your homework, right? Your homework asks for prediction or does it ask for confidence? This should be prediction. Yeah, this should be prediction. So if you want confidence, I'd have to think about how to get confidence. So this is something, so usually as a rule of thumb, most things that you would do very commonly are automatically done for you in R. So this is something you want to do all that commonly, is generate a confidence interval around your probability.
Is that for odds? Is that for probability?
This is for probability because I gave it this type equals response. So that is saying that the probability that it's a red wine is like 0.89. Sure.
So the lower and the upper represent like the lower and upper bound of the prediction.
Yeah.
Correct.
Yeah.
Could you give me an example how to like that interpretation? Just like
yeah, you can say that like with 95% confidence, I know that like the true probability lies within this range. Okay. And there's a little bit, this starts so you're starting to get to the point where where some of the background like knowledge and statistics becomes more and more important, right? So there's different ways you can do this sort of thing, right? So there's some So you're sort of assuming, right, that there is some probability that it's a 0 or a 1 and that we can predict that probability, right? We are assuming it's not just like a, oh, once you get to this point, it's different and things like that. Okay. So it is a little bit, it gets a little more complicated, but yeah, that's more or less what's going to happen. Is that it's fine, that probability is within that bound. Or this is 90% confidence interval. I know I said 95. Anybody have any other questions? Sure. That's the z-value for a 90% confidence interval. I'll look up how to call that command in R. I don't remember. Do you have a question? Oh, that says times predict, so PREDS, which is what I named the prediction. And when I called that prediction, I made sure to keep track of the standard error by writing se.fit equals true. And then, so that's the, yeah, that's just an asterisk, so that's times the standard error of the prediction, which is more or less just the same formula for a prediction interval or confidence interval that we've always seen before. Okay. Okay, if everybody's okay, I'm going to keep going. All right. Okay. Okay. So all of that was a lot, right? But that was only for one variable. However, it's really nice because just like how when you go from single variable regression to multivariable linear regression, everything stays the same, right? You don't have to worry about all your interpretations changing, anything like that. It's going to be the same thing here. But, you know, things become not as nice. It's a little harder to fit large logistic regression models than it is large linear regression models. So let's say I want to use every single variable I have available to me. I'm sorry if that's a little hard to see, but what that says is GLM, type, then the little tilde, and then a period. So if you just type a period in R after that tilde, it'll just tell R, hey, go and get me every single variable available within that data frame. Okay, so that's just there so I don't have to do what I do in line 47 where I write out every single variable. Okay, it just saves you some time and space, and it makes it a little more readable. And then again, make sure you have that family equals binomial. I'm telling it that I'm getting my data from lines. And I can run summary on that just like I did before. And hey, if I run summary, it doesn't, you know, it's just this huge thing, right? So just like before, now we have coefficient term, now we have the coefficients. And so, for example, the log odds of whether it's a white line will increase by 2.617 if you increase citric acid by 1, holding everything else constant. Okay, so the same exact interpretation as it was in linear regression. Okay. Additionally, you can call VIF on the model, just like you have before, if you want it. So multicollinearity is still a concern with logistic regression. Okay, so you should check for that. And if you you can run the pairs function if you want and get a whole bunch of graphs, but they're basically impossible to read. So just run the VIF function. Okay. So when are we concerned about VIF? If we're concerned about multicollinearity, if the VIF is above what? Yeah, 5. Right. So which one of these is concerning? There's actually two of them that are concerning, right? Both the quality and the alcohol content are both a little bit concerning, right?
Is there a package we need to put in?
Car? I think it's in car. Yeah, it's in car because that's the only one I have loaded right now. Sure.
What's the development that makes it like that you have to throw it out in about 5?
Oh, so if you don't want more or less, so the VIF tells you whether or not maybe like your third variable is correlated with all the other variables in your data set. And what it's literally doing is regressing like citric acid on every other variable in the data set and seeing if all the other variables do a good job of indicating citric acid. If they do, then you're sort of like counting the effect multiple times, which you don't need to do in the first place. And the problem with it is that if you have multicollinearity, it will make your p-values much larger than they actually should be. So we generally want to throw those out. And you should throw them out one at a time. So we're just going to throw them out one at a time, right? Because when you throw out density, because it has the highest VIF, you might find that alcohol has an acceptable VIF. So let's try that. So I'm going to rerun the model without density in it. And R throws me a warning saying that there's probabilities with numerically 0 or 1. And that's just because something in this data set has a probability of like 0.9 to 9 to 9 to 9 to 9. Right? And that's essentially 1, and R just makes sure you know that that's happening. Because in real data, you will not be able to predict things nearly as well as I'm doing right now with this wine data set. Right? Because there's some physical reasoning as to why, like red wines may have like a lower sugar content and things like that, just because that's the way they are, right? So I threw out density and I called the VIF function again, and everything looks nice. So I'm going to keep going. I'm going to keep going with the model. Okay. All right. And since I already talked about the coefficients and how you interpret them, I'm going to go on to the next bit of the homework. Okay. So does anybody else have any other questions? Sure. Make sure that you're giving it data equals lines, and make sure that you're giving it, you don't have my data, right? Yeah. So I'll distribute the data. So if you want to try this out on your own, I'll distribute the data. Okay. And just like before, we can go and generate a pseudo R squared, and then if you check this, it's way better than it was before, right? Now it's like 0.91. And remember, if like 0.2 to 0.4 is considered good, this is extremely good, and it's because this is something that's very easy to predict. All right, everybody doing okay? All right. Okay. So here's the thing, right? So pseudo R squared doesn't really consider the size of the data set. I mean, it's the number of parameters in the model, so we might be worried about that, right? So we could try out a lot of different models and see how they do, but as you might have noticed, there's like 12 variables in this model, right? There's 12 variables available to us to be used. So that would give you 2 to the 12th options for your models, which is like 4,000. Okay, so you don't want to check 4,000 models by hand. That's few enough that you could actually make R check every model for you automatically, and I'll do that right at the end. But something that's a little bit easier to do and that's talked about in your readings a lot is this idea of forward and backward selection. Okay. So forward selection essentially just starts out with nothing in the model and then adds a variable that it thinks is the best based on the p-values. And then adds another one, and adds another one, and adds another one until you get to the point where it doesn't really find another good variable to add. Backwards selection works the reverse. It starts out with everything, and then removes them one at a time, usually based on p-value and the resulting statistics of the models. And by default, this function uses AIC until it kind of converges on a model that you don't want to remove anything else from that model because it makes your AIC increase, or you don't want to remove anything from that model because all the p-values are significant. Okay? And there's different ways you can do. So you can do these step-based selection methods depending on what you want to do. You can base it purely on the p-values. You can base it on R squared, adjusted R squared, AIC, BIC, whatever you really want. But this by default just looks at AIC. Okay? And so when you run these automatic model selection tools, it's important to note two things. One is that you're checking something that so every time you run one of these regressions, you're risking having like a type 1 or a type 2 error, right? So even if that probability is very small, when you're running these regressions, when you're running like 1,000 regressions, that becomes concerning, right? Because you've done it so many times, it might have happened. So when you get your model at the end, you should always check it. Check it for things like if the p-values are significant, if your residuals make sense, if your assumptions still hold, all of these things before. It's very difficult to make a computer automatically check these assumptions for you. All right, so in R, it's fairly easy to do this based on the step function. So you have to give it a null and a full model. And with the null model, I just say tilde 1, because that just says, hey, the only thing I want in that model is the intercept. And then with the full model, you'll notice, again, I'm calling it type tilde and then a period, because that says, hey, just grab all the variables in my data set. And that's all you really have to do to set that part up. So you have a question?
Yeah, could you explain what exactly this is doing? Null, full, and final? Is this forward and backwards?
Yeah, I'm getting there. Okay. So the null model is the model with nothing, and the full model is the model with everything. And it's pretty likely that you don't want to be on either side of that, right? You want to be somewhere in the middle. But you have to give R some things to look through. So you have to give it a starting point, which if you're doing forward selection is the null model, and you have to give it an ending point, which if you're doing forward selection is the full model. And it may end early based on the p-values and the AIC and things like that. Okay. So this function works by, you just call step, and then you give it the full model. So I'm doing backward selection. So I'm giving it the full model, and then telling it that the scope of things to look through is the lower end of that scope is the null model, and the upper end of that scope is the full model. And then I'm telling it, hey, do backward selection based on that direction. If you want forward selection, type direction equals forward. Okay. Real quick, you can definitely get different results if you do forward selection versus backwards selection. That's okay, it happens. There's not necessarily like one model. There is, so we usually think that there is a true model, but the forward selection may get you a model that's pretty good, and the backward selection gets you a model that's pretty good, and as long as they're about the same, it doesn't really matter. Okay. So I'm just going to run this. And it takes R just a second to kind of hack through this, and my computer is pretty old. Again, it throws me a bunch of warnings. And I'm just going to go ahead and call the summary final on it. So you'll notice a couple of things here. One is that it worked out very nicely. All of our parameters were significant. And it gives us as we'll see in a second, it has a better AIC, and it has a better pseudo R squared. And you'll also notice some interesting things. One is that a minute ago we threw out density because it had a really high VIF, right? But actually, based on this, it includes density and instead throws something else out, right? So maybe we want to check the VIFs of this model just to make sure there's no problems. So we can do that real quick. And we find out that, yeah, all the VIFs, they look fine. So you should check these things when you run these automatic selection tools. Okay. All right, so to look at this resulting model a little bit more, so let's look at this new model has an AIC of 449, whereas the model that I manually built a second ago where I threw out density has an AIC of 610. So which one do we prefer? What? Yeah, we prefer final, right? Because the AIC is smaller, right? We prefer smaller AIC. We prefer smaller BIC, okay? So we can also look at the pseudo R squareds. So I can, again, calculate a pseudo R for the final model, and then I'll print it. We find, hey, the pseudo R for the final model is better than the pseudo R for the one I did manually, right? Because we prefer higher pseudo R squareds. All right? Is that okay? So that's one way you can kind of compare these models. Look at the AIC, look at the pseudo R's, and see how they do. All right? Sure.
So if we do the automatic with like the step and then you get p-values that are like greater than 0.05, should you still manually take those out?
So what I would do is I would manually take it out and then see how much worse the model became. So you might find that when you take that variable out that's supposedly not significant, the model gets way worse in terms of like AIC and pseudo-R and things like that. That's worrying when that happens, but it might imply that there's more problems in the way your data is. You might have outliers, things like that. It should work out reasonably, especially on your homework. It should work reasonably well. If you take a couple of them out, it should be fine. It shouldn't change the AIC that much. Okay. All right. So this okay? Everything makes sense so far? So we just told R, hey, give me a good model, and then I just double checked it manually to make sure that the things that a computer is bad at doing were fine. So the computer has trouble checking. You can't really tell it to check diff of everything and things like that. So it's good to check these things manually. All right. Anybody have any questions about automatic model selection? Sure.
If you get ones that aren't statistically significant using a stepwise or something like that, should you just go ahead and manually take those out, or assume they were put there for a good reason?
I would manually take them out and see how much it affected AIC.
Okay.
So there's there's slightly more advanced ways to do this sort of thing for variable selection. Usually today, most people use what's called a lasso regression to do variable selection, which ends up working a little bit better than this does most of the time. But the biggest draw to these forward and backward selection methods that make them worth it is that when you're doing these real data sets, so for example, if you're looking at something like medical data and you have an unbelievable amount of information about every single one of your patients, you might have like 500 variables or something. That's 2 to the 500 models. So that's the big draw to these step methods, is that it can go through and check all these things reasonably quickly. Okay, so and you kind of do sacrifice a bit of things where, sometimes it comes out and things aren't significant, or sometimes it comes out and your BIFs are wrong. But it's kind of worth it for that. Okay. Everybody okay so far? Sure.
The manual pseudo-R.
Oh, I kind of skipped over that a second ago, but it's just the pseudo-R for the second model I built.
Not final.
Not final. So it's the model I built manually by removing density because it had a really high VIF.
And then final kept that.
Yeah, but it throws out, I think, fixed acidity and then something else. And you'll notice, interestingly, this model is smaller than the model I built manually, but it works better. So we've gotten rid of model complexity and gotten something that works better, which is great. That's something we'd love to see. Okay. All right. All right, so I'm going to kind of finish things up. So the other problem we have is, we can say, hey, how good is our model really? So one of the things you'll find when you start doing more complicated modeling techniques like this, and like the forecasting models you'll start doing in the next couple of weeks, is that you really need something to compare them to. So we usually compare this sort of logistic regression model with just this naive prediction where we say, okay, I'm going to say which one happens the most, and then I'm just going to say, okay, no matter what the variables are, it's going to be that one. And in this case, there's more white wine in the data set than red wine, right? So if I predicted white wine every time, let's see how well we do. So you can do this by kind of calling like some wines type equals red and some wines type equals white. And R is pretty smart, and we'll just pick up that because trues are interpreted as ones. It'll add those all together for you and give you a number. And there's significantly more white wine in the data set than red. So if you just predicted white wine every time, it'd give you about 75% accuracy, which is pretty good, right? The worst thing you could do is 50% accuracy, right? Because if it was less than 50% accuracy, you would have just predicted the other one all the time. All right, everybody okay with that? I'm going to run these and then talk about them. So let's try out our model and see how well it does. So let's say the ones we predict to be red are the ones where the final model predicts it to have a probability of less than 0.5, because red is 0 in our data set. So if we say, so the predicted reds are all of those, and then the ones that are actually red are wines type is equal to red, right? And then if we kind of calculate a final accuracy based on that, we can say, okay, well, where is it actually red when we predict it to be a red wine? So that's what this part does with this predicted red equals actual red, and then divided by the number of wines in the data set. And we actually do very, very well, right? We get like 99%, right? And you're never going to get that in real life. So don't strive to be getting like 99% prediction. It's not going to happen. It's happening here because there's some physical laws about red wine's more acidic or has less sugar or something. Like I said, I don't really know that much about wines. Okay, that all right? So we did a lot better than our naive model, right? Our naive model, where we just predicted white every time, gave us like 75% accuracy. We actually use our model, we're getting like 99% accuracy. Okay, and this is specifically the accuracy of predicting red wines. So you have a question?
Yeah, so this as well as the pseudo R squared, how would you use either of those when you talk about practical significance?
Practical significance of your model? Is that what you mean? That's really accurate, right?
Okay.
So that means your model's practically very useful.
Okay.
Pseudo R, like I said, I don't think it's covered in your book, and I'm hoping the professors talk about it a little more in the next day or two. But pseudo R is, from what I understand, is considered good if it's between like 0.2 and 0.4. So you should.
And would just equate that to practical significance.
Yeah, that's fine.
Okay.
Yeah. Well,
And
it is a statistical, so that is a statistical. I'd have to think about that if you can use pseudo R. I would rather use this for practical significance than I would pseudo R.
And just that it's like a decent degree larger than your naive prediction.
Yeah, absolutely. Yeah, and I mean, it is what it is. Like, you know, your naive prediction's right 75% of the time. If this complicated model was only right like 77% of the time, that may not be worth it to you. You may just say, whatever, I'm not going to try to build this complicated model all the time. Okay. All right. Everybody okay? I'm just going to show one other thing and then we'll be done, and I'll answer any questions anybody has for like 15 minutes or so. All right, so the other way we talked about doing automatic model selection is with Leaps. So Leaps is another package in R. Like I said earlier, right? There's 13 variables in the model, which is like 4,000 potential models, which sounds like a lot, but for a computer, it's really not. So we can actually crunch through all of those by using the Leaps package. And so you can work through the Leaps package just by loading it and then calling reg subsets. So that stands for regression subsets. And then give it type, and then all the variables in the model, or the variables you want to look at least, and then tell it the family is. I know. Oh, did I not? Sorry, I did want to. I actually wanted to bring this up. So you can call it that. You can. So usually you can do this to do linear regression, right? And normally the way you go from like linear regression to this logistic regression is giving it like a family equals binomial. So you'll find that the Leaps package, as far as I know, doesn't do logistic regression. Okay. So stick to the steps thing for logistic regression. Use reg subsets. Reg subsets is great because it checks every single model. And for ordinary linear models, that's easy to do. Traditional linear regression is way faster than logistic regression in terms of computation time for a computer. So you can crunch through lots and lots and lots of linear models. But it won't work for logistic regression, as far as I know. I'll check more into that, but yeah. Question?
Can I ask you something about homework 6?
Aren't we on homework 6?
No, well, like, I guess, like, data of that instead of...
Sure. Let me finish. Does anybody have any questions about how to do this? Everybody okay? So you should find that everything we've talked about over the last hour should sync up really well with your homework. Okay? So you should be fine. And I'll take questions about anything for like the next 10 or 15 minutes, but this is going to be the end of the recording. Okay.
You'll post that the next day or so. Or